Most hikers and amateur rockhounds walk straight past the very rocks that conceal the clearest surface signals of diamond-hosting formations. In volcanic fields where ancient eruptions once punched through the Earth's mantle, small fragments of kimberlite or lamproite often scatter into visible terrain. But their drab color and crumbly texture mean they're usually mistaken for weathered basalt or construction rubble. The key to understanding what gets overlooked begins with the nature of the volcanic pipes themselves. Unlike the dramatic lava flows of surface volcanoes, these pipes are ancient, vertical conduits formed by gas-charged explosive events that pulled mantle material up to the surface. What remains today are eroded stubs of those pipes, often surrounded by later sediment or glacial till. That means the remnants, nodules, xenocrysts, altered matrix, are often exposed only in fragments, embedded in otherwise nondescript terrain. And that's where most people miss the opportunity. They ignore soft, blue-gray clasts on roadsides or under sparse vegetation that don't sparkle, but do signal potential. Kimberlite, the primary host rock of natural diamonds, weathers quickly at the surface. Its blue ground phase, the fresher, deeper matrix, is a soft, clay-rich rock that tends to turn yellow as it oxidizes in air and rain. These yellowed pieces, often the first visible indicators, are easily mistaken for claystone or degraded shale. But one field cue stands out: their relative softness combined with a chalky, sometimes greasy texture and a faint peppering of black mineral grains. That mineral peppering isn't random. It can include ilmenite, pyrope, garnet, or chromite, all indicators of deeper volcanic transport. Another giveaway lies in how these fragments break. Unlike hard igneous rocks like granite or basalt that cleave cleanly, weathered kimberlite tends to crumble into angular chips with an almost waxy break pattern. Pick up a piece and rub it between your fingers. If it leaves a faint, powdery smear with visible specks, stop. That's your signal to test further. Yet even experienced collectors often pass over lamproite fields, whose rocks can mimic vesicular basalt at a glance. Lamproites, while rarer, can also host gem-quality diamonds, notably the Argyle deposit in Australia. In the field, their distinctive features include a greenish hue, glassy vesicles, and abundant mica or olivine. When broken, lamproites often emit a faint sulfuric odor, another sensory clue most overlook. Each misstep over such rocks is a lost chance to catch a diamond-bearing formation at the surface without digging. But once that clue is registered, a different question takes shape. How can we separate these candidate fragments from the sea of volcanic detritus that crowds most ancient fields? The answer lies in a visual test most people already know, but rarely apply correctly. A common volcanic rock may sit inert for decades in a collector's stash or roadside cut, untested and undervalued, simply because no one noticed its surface betrayals. Yet under close visual scrutiny, diamond-hosting rocks display subtle but diagnostic differences. The first gate is luster and texture. What appears dull at a glance may conceal the mineral fingerprint of a kimberlite or lamproite body. Begin with the surface. True kimberlite in its weathered state often exhibits an earthy to subvitreous luster, punctuated by glints of metallic or glassy grains. These grains, ilmenite, pyrope, and chromite, appear as peppery inclusions, not aligned like a gneiss or foliated schist, but scattered through the matrix like ground spices in dough. The matrix itself may be soft and light, with a tendency to flake when scratched with a knife blade, significantly softer than quartz or feldspar-bearing rocks. Color is a trap. Most people expect vibrant tones, but the best clues are muted: pale blue to gray for fresh kimberlite, yellow to brown for oxidized zones. The contrast matters. A stone with a greenish tint might suggest olivine content, common in kimberlite and lamproite, but don't rely on color alone. Look at habit, the physical form and context. Is the rock nodular, brecciated, or vesicular? Does it show any angular inclusions or signs of having transported deeper material? Among volcanic rocks, only a few bear mantle-sourced xenocrysts. In kimberlite, you may find coarse, rounded grains of pyrope garnet, a rich purplish red under sunlight, or dark chrome diopside crystals. These are never orderly. They present as embedded, sometimes fractured, and are often mistaken for industrial garnet or crushed slag. Lamproite, on the other hand, may show larger, glassy vesicles with greasy green mica or perovskite traces, often flecked with black specks of iron-rich minerals. The weight-in-hand test offers another edge. Pick up 2 stones of equal size, one basalt, one possible kimberlite. The kimberlite often feels subtly lighter due to its fine-ground, altered matrix, yet can contain dense mineral grains that create odd imbalance. If a rock crumbles in hand but still carries weighty specks or crystals, it's time to sample. This moment of visual separation is critical. It filters out 90% of the noise in volcanic rubble. You're not looking for perfection or sparkle, you're looking for inconsistency. Anything too uniform is likely junk. Anything with a gritty mix of textures and embedded grains, especially in crumbly or greasy matrix, is worth closer investigation. But once you've gathered a handful of potential candidates, the next step escalates, choosing a search area where these clues cluster and understanding what the terrain itself is telling you about buried potential. Because where surface float concentrates, a deeper structure may lie directly beneath your feet or miles upslope. Standing on the surface of a volcanic field offers no obvious sign that diamonds might lie below. But the Earth remembers. Erosion, glaciation, and weathering may have scattered the surface record, but the subsurface structure of diamond-bearing pipes leaves repeatable, mappable clues. The critical difference lies in understanding how these pipes form and where they most likely occur. Diamond pipes, particularly kimberlite and lamproite bodies, are almost always rooted in stable cratonic zones, ancient continental interiors that haven't seen tectonic upheaval in over 1 billion years. These regions are geologically quiet, but host some of the deepest lithospheric roots on the planet. It's in these roots under high pressure and low temperature that diamonds crystallize. When volatile-rich magma punches through, it carries pieces of that mantle, and any diamonds upwards at supersonic speed, freezing their contents in volcanic conduits. That eruption column isn't uniform. The classic kimberlite pipe has a carrot-like shape, narrow at depth, widening near the surface, then constricted again by erosion and sedimentation. So the original explosive vent might be buried or eroded, but its debris, the kimberlite float, can be traced along slopes in creek beds and around collapsed structures. Start with topographic lows. While many associate volcanoes with peaks, diamond-bearing pipes are often subtle depressions or circular valleys. This is due to the rapid weathering of kimberlite and lamproite, which break down faster than surrounding host rock. A ring of elevated, more resistant country rock often surrounds a softer, vegetated center. Remote sensing has improved the ability to detect these zones, but in the field you rely on contour logic and hydrology. Water follows the path of least resistance, and over centuries, creeks often carve through the softer ground of pipe zones. Look for anomalous meanders, oxbows, or standing water in seemingly flat terrain. Any stream that carves a sharp bend around a low mound could be diverting around a degraded volcanic throat. Another key lies in the distribution of float. As you move upslope, track changes in rock type and mineral density. A rising concentration of indicator minerals, pyrope, garnet, chromite, ilmenite, along a given line suggests you're moving closer to the source. Plot these changes. Use a simple grid and GPS pins, sampling at fixed intervals and noting the presence or absence of key traits. A buried pipe might be within 10 to 30 meters of the surface, or as deep as 100 depending on overburden and glacial cover. But signs often leak out. A linear train of garnet-rich clasts, a brecciated dike intersecting bedrock, or even a faint sulfurous smell from altered ultramafics after rainfall. Lamproite complicates the picture. These pipes can be shallower, sometimes horizontal, and are more chemically altered. But their geochemical fingerprint often leaks into surface soils. You'll find elevated levels of potassium, magnesium, and sometimes rare earths in surrounding plants or water bodies. Mark these zones. Photograph, label, and cross-reference with regional geological maps if available. Many public surveys outline potential pipe zones, even unconfirmed ones, which can serve as field leads. But no map replaces what your feet and eyes gather on the ground. Most raw diamonds are invisible at the surface, hidden deep within the matrix of eroded volcanic pipes. But their sentinels, the indicator minerals, arrive first. These are the deep origin crystals that ascend with the magma and survive the violent journey to the surface. While a diamond may remain locked in host rock or shattered by erosion, its companions, pyrope, garnet, chromite, ilmenite, spinel, and chrome diopside, often escape and concentrate in streams, soils, and surface float. Field prospecting for diamonds never starts with the gem itself. It starts with these proxies, each one carrying geochemical signals that point to a possible kimberlite or lamproite source. Spotting them requires both trained vision and a methodical approach to collection. Begin with pyrope garnet. Unlike the common almandine garnet found in metamorphic schists, pyrope has a rich, purplish red to violet hue, sometimes with a slight transparency when held against light. The best field clue is what garnet does under pressure. Its edges resist abrasion. So if you're sieving creek sediment and find a round, glassy red grain that hasn't dulled from transport, pay attention. In some regions, especially southern Africa and Siberia, pyrope garnets are tinted with chromium, giving them a stronger hue and higher diagnostic value. Chromite and ilmenite look less glamorous, but they carry more weight, literally and diagnostically. Chromite appears as black, submetallic grains with high specific gravity and weak magnetic response. Ilmenite, a titanium iron oxide, often has a bluish-black sheen and responds faintly to a magnet. Both can be mistaken for iron sand or slag, especially in industrial regions, but their habit, rounded but dense grains, helps distinguish them. To collect, use a sluice or simple batte pan with a 20 0.85 and 40 0.425 mesh. Sample upstream and down along a creek bed, ideally within 1 km of your suspected pipe. Wash the concentrate and observe what settles in the heavy fraction. Look for purple-red garnet glints, metallic black specks, and olive-green translucent fragments. If you're seeing these in meaningful numbers, say 5-10 grains per pan in multiple spots, you're close to a significant source. But beware the zircon trap. Zircon is a common accessory mineral in many volcanic and metamorphic settings. It can appear as clear, high-luster grains and even fluoresce under UV, leading to false assumptions about diamond presence. Unlike true indicators, zircon often clusters in felsic rock contexts and lacks the associated chromite-ilmenite suite. One quick distinction: zircon is nearly always smaller and perfectly euhedral, tiny glass-like prisms, whereas diamond indicators tend to be rounded, fractured, or embedded in altered matrix. Field notebooks should log every pan sample, GPS coordinate, and mineral estimate. Photographs under natural and UV light provide visual records for later comparison. Samples with more than one indicator mineral, especially pyrope plus ilmenite or chromite, are flagged as high-value leads. Before you start swinging a sledgehammer at every promising outcrop, one of the simplest, most decisive tools in your field kit can save you hours: a strong handheld magnet. In the search for diamond-hosting rocks, magnetic behavior acts as an early filter, especially when evaluating the presence of ilmenite and magnetite, two key indicator minerals that often appear in kimberlitic or lamproitic rocks. But this test, though quick, is nuanced. Ilmenite, a titanium iron oxide, is weakly magnetic. It won't leap to your magnet, but it may twitch when the magnet is moved close or dragged across the sample's surface. Magnetite, on the other hand, responds strongly. It clings instantly, sometimes even causing the magnet to vibrate if grains are loosely embedded in soil or crumbly rock. The presence of either one matters. Magnetite suggests ultramafic or mafic parentage, common in volcanic conduits, while ilmenite is more directly tied to kimberlite fertility. To perform the test in the field, use a neodymium magnet, ideally encased in plastic or tape to avoid picking up fine iron dust that obscures results. Pass the magnet slowly over your concentrate or rock surface. For loose material, scatter a thin layer in a plastic pan and run the magnet just above it. Grains that roll or drag subtly are weakly magnetic, possible ilmenite. Grains that jump or stick are likely magnetite or iron-rich fragments. A second layer of analysis comes from combining magnetic behavior with color and luster. Ilmenite often appears as bluish-black or steely, with a dull metallic sheen. It can be confused with hematite, which is non-magnetic, or chromite, which is only slightly magnetic. Chromite itself may respond faintly, but it tends to be more opaque and rounded. If your sample shows a mix of magnetic grains, some sticking, some not, you may be in a zone with both magnetite and ilmenite-bearing kimberlite float. Lamproitic rocks present differently. They may carry little to no magnetite, and their indicator suite often includes perovskite or leucoxene, neither of which respond to magnets. A negative magnet test doesn't eliminate a sample from contention, but a positive one, especially when accompanied by garnet or spinel, raises the priority of that zone. It's also useful to magnet test brecciated rocks and host matrix fragments. If you observe patches or veins where only part of the rock responds, this suggests an intrusive body or a relict fragment embedded within surrounding material. These hybrid textures often mark the outer rim of an eroded pipe or dike system. Don't stop at float. Magnet test in situ boulders, road cuts, and stream bank exposures. Many times, an entire slope may be covered in volcanic tuff or glacial till, but but only one layer within it contains magnetically active fragments. That's your lead horizon. However, magnetic response alone is not conclusive. Some iron slags, man-made materials, and basaltic rocks give false positives. That's why after isolating magnetically responsive fragments, you must fracture the rock itself. The interior structure, mineral distribution, and break pattern will tell you if you're dealing with a true volcanic conduit, particularly one altered enough to weather diamonds to the surface. The sound a rock makes when it splits can be more telling than its color. Many diamond-hosting rocks, especially weathered kimberlite and lamproite, shatter with a muffled pop rather than a sharp crack. That's your first clue. But intelligent breakage isn't about brute force. It's about where and how you strike to reveal the diagnostic internal structure of the host material. Fresh kimberlite, known as blue ground, typically breaks into crumbly fragments with a chalky consistency. The break is often uneven, with soft zones surrounding harder embedded grains. These harder grains are what matter. If you see angular or rounded mineral inclusions, especially purplish garnets, dark chromite, or greenish diopside, you're not just holding a volcanic rock. You're holding mantle cargo. Lamproite behaves differently. It's more glassy and vesicular, meaning it may break along bubbly voids or display fracture planes around altered phenocrysts. When fractured, lamproite sometimes emits a faint sulfur smell due to its elevated potassium and volatile content, especially when the rock is moist or sun-warmed. If you detect this odor after splitting, it's a flag to investigate further. Always break near the freshest face. Avoid testing heavily weathered surfaces where oxidation may disguise mineral content. Use a cold chisel and controlled strikes to avoid pulverizing delicate inclusions. Examine both halves immediately. True indicator minerals often appear as fractured cross-sections, pyrope as deep red crescent shapes, chromite as glossy black lenses, and ilmenite as metallic smears within the matrix. Their distribution isn't random. In legitimate kimberlite, they appear throughout, not just on the surface. Note also the presence of xenoliths, foreign rock fragments carried from the mantle. Peridotite or eclogite nodules embedded in kimberlite are strong evidence of deep mantle transport. These nodules may look like greenish or granular patches surrounded by fine-grained volcanic groundmass. If you spot one, remove it whole and document it. Some of the world's most important diamond finds have come from rocks containing visible peridotitic inclusions. The break test also helps identify fakes. Many industrial slags or concretes with iron-rich flecks mimic indicator textures, but they break with a hollow ring and expose air pockets or slag bubbles inside, dead giveaways. Similarly, basalt may carry vesicles but lacks the peppered, greasy matrix typical of altered kimberlite or lamproite. Breaking volcanic rock exposes internal structure, but it's in the dust and chips, what most discard, that vital clues concentrate. The key is to isolate the heavy mineral fraction from your crushed rock using graded sieves. This transforms raw fragments into measurable, sortable concentrate, allowing you to separate real diamond indicators from background noise. Start by air drying your broken rock in sunlight or over low heat. Moisture skews particle behavior in sieving, so ensure everything is bone dry. Then crush the samples to a grain size no larger than 2 using a jaw crusher or a steel mortar and pestle. Never use ceramic tools, as they can contaminate results with high aluminum residues. Your goal isn't to pulverize, it's to liberate dense grains without destroying them. Pass the crushed material through a nested sieve stack. Use a coarse 20 mesh, approximately 0, 85 on top and a finer 40, approximately 0, 425 beneath. The 0, 425 fines can be saved for X-ray diffraction or assay work later, but most of your diagnostic minerals will settle between these two sizes. Collect and inspect the 0, 425 0, 85 fraction, the heavy zone. Place this intermediate fraction in a gold pan and submerge it in clean water. Tilt and swirl gently, washing away the lighter matrix until only the heavy minerals remain. In a good kimberlite sample, you'll see rounded red-purple grains, pyrope garnet. Black submetallic grains, chromite, ilmenite. Green translucent fragments, chrome diopside. Possibly clear or white angular shards. These demand further testing. Hold the pan under direct sunlight and observe the grains. Pyrope glints with a glassy luster. Chromite holds a dull sheen and may streak brown-black. Ilmenite shows subtle bluish-gray highlights and may be faintly magnetic, as confirmed by a magnet wand passed above the concentrate. If you find a range of colors and densities, especially multiple indicator types in a single pan, you're likely close to a productive source. Dry the concentrate on clean filter paper and inspect under 10x 30x magnification. Count the number of each indicator grain type. A pan with 3-5 pyropes and 1-2 ilmenites is marginal. One with 10+ pyropes, chromite, and diopside from a single 10-20 kg rock sample is high priority. Log these values per sample and grid square. Repeatability is critical. If multiple samples from the same site yield similar concentrations, the odds of pipe proximity rise significantly. Lamproite samples yield different concentrates. You may see vesicular grains with embedded mica, light brown perovskite or leucoxene, pale green olivine fragments. Avoid misidentifying magnetite or dark basalt fragments as indicators. Run a magnet over all dried concentrates and remove strongly magnetic material. It often includes irrelevant ferromagnetic grains or furnace slag. Glass fragments, especially green or clear ones, can also sneak into samples in areas with historical waste. Always test these optically and by density before considering them candidates. A freshly panned concentrate may glint with promise, but without testing its deeper physical properties, you're only seeing half the story. UV fluorescence and thermal conductivity tools, though neither definitive alone, offer quick, non-destructive ways to sort real candidates from imposters. But these tests, widely misunderstood, can yield misleading results if used out of context. Knowing when and how to apply them is critical. Start with long-wave UV, approximately 365 nm. True diamonds often fluoresce under this light, typically glowing blue or bluish-white due to nitrogen impurities in the crystal lattice. In the field, shine a portable UV lamp on your dried concentrate in a shaded area or at dusk. Watch for flashes of color. Most rocks won't react. But if a grain fluoresces brightly and consistently under both sides of a 365 nm beam, stop and isolate it. Caution is key here. Many non-diamond materials also fluoresce. Some zircons glow yellow, some feldspars emit faint pink. Even synthetic materials like glass slag or moissanite can fluoresce under UV, leading to costly false positives. To screen them out, check whether the reaction is uniform and stable. Diamonds tend to fluoresce in a stable tone across their whole surface. In contrast, most imitators flash unevenly or fade quickly after initial exposure. Next, move to thermal conductivity testing. Handheld diamond testers, often pen-sized devices, detect how quickly heat transfers through a material. Diamonds conduct heat rapidly due to their crystalline structure, producing a near-instantaneous spike on the readout. To use the tester, ensure the grain is clean and seated firmly on a non-conductive surface. Gently press the tip of the probe against it. If the indicator lights up or the digital readout spikes, you have a candidate. Yet even this test isn't foolproof. Moissanite, a synthetic simulant, can mimic diamond conductivity under thermal probes. To counter this, use a dual-mode tester that includes electrical conductivity. Diamonds are poor electrical conductors, while moissanite conducts electricity slightly. If a stone registers high thermal but also conducts electricity, it's almost certainly not diamond. The best field strategy is combinatory. Let's say a grain fluoresces blue under UV, shows strong thermal conductivity but doesn't conduct electricity. That triple match flags a strong candidate. But if it fluoresces yellow, conducts heat, and responds to electricity, it's likely synthetic or zircon-based. Each layer filters noise. Weight and shape also play roles. Diamonds have a specific gravity near 3.52. If a suspected grain feels unusually light or heavy compared to expectation, test its density later via water displacement. Likewise, check for double refraction under a 10x loop. Moissanite often displays facet doubling, fine but visible under magnification, while diamonds show single, sharp edges. These handheld tests are especially powerful when applied to sieved concentrate. Instead of testing hundreds of grains randomly, use your UV light to pre-sort, your loop to assess clarity and habit, and your thermal tester to confirm shortlists. Record every result with photo documentation, especially for grains showing multiple diagnostic hits. Despite their utility, these tests don't replace full mineralogical confirmation. In some cases, UV and thermal tools can falsely eliminate real microdiamonds with atypical properties. That's why field success ultimately depends on test pattern repeatability. If you find multiple grains in multiple samples all showing matching traits, UV fluorescence, non-conductivity, and thermal response, you're closing in on something real. Few setbacks sting more than learning a promising concentrate, fluorescent, dense, conductive, was loaded with zircon or high-index glass. These imposters pass early field tests with unsettling ease, especially in weathered terrains or glacial, till zones where true diamond indicators and mimics mix freely. Zircon, in particular, is a master of deception. Zircon forms naturally in a wide range of igneous rocks, especially felsic varieties like granite and syenite. It survives weathering and erosion, resists acid, and concentrates in heavy mineral separates. Its hardness, 7.5 on Mohs, and high density, ~4, 6, allow it to sink alongside garnet, ilmenite, and even small diamonds during panning. Under UV, it may fluoresce yellow or orange, rarely blue, but still close enough to sow confusion in poor lighting. In sieved material, zircon appears as small, glassy grains, often colorless or light brown, with a tetragonal square cross-section crystal habit when fresh, but most field samples present as rounded or abraded, removing this useful cue. So how do you sort zircon from diamond candidates in the field? First, examine luster. Diamonds exhibit an adamantine brilliance that seems to glow from within, subtle but noticeable under sunlight or LED. Zircon, despite being highly refractive, lacks that depth. Its luster is glassy, not glowing. But this test is subjective and breaks down with small or worn grains. More reliable is facetage behavior. Under a 10x, 20x loop, diamonds show sharp, crisp boundaries, no doubling. Zircon can display mild birefringence, double refraction, especially along elongated axes. You may see a faint doubling of facet edges or interior features, a telltale sign that you're not dealing with diamond. Then there's the magnet trap. Zircon is non-magnetic like diamond, but often travels with weakly magnetic heavy minerals. If you find grains with identical UV and density behavior, but only some react to a magnet sweep, those magnetic grains may be ilmenite, the others could be zircon or glass. This diversity in response helps sort your sample's content. Glass, especially high-index varieties from industrial waste or obsidian-like natural sources, poses an even subtler risk. It mimics diamond in luster, hardness, if annealed, and even weight. Some fluorescent glass shards glow blue or green under UV. But they're nearly always curved, show conchoidal fracture, and often carry surface bubbles or swirls, best spotted under loupe or microscope. If you detect curvature or flow lines in a grain, discard it as probable glass. Another trick: perform a scratch test on quartz. Glass may scratch it, but diamonds will do so cleanly, leaving crisp lines. Glass often leaves irregular or flaked marks. Still, this risks damaging your candidate, so use only on borderline cases with no other distinguishing traits. In some terrains, especially near human settlements or historical mining sites, zircon and glass can dominate heavy concentrates. That's why repeatability across samples is essential. A single UV-positive grain near a road cut is likely debris. 10 grains of consistent color, shape, and behavior from a remote stream's upper fork, that's a pattern. Don't let the confusion discourage you. Each false positive sharpens your eye and improves your workflow. By catching zircon and glass early, you prevent costly lab testing and misallocated effort. But even as you grow better at ruling out fakes, the question tightens. What test combination offers confirmation without destroying the specimen? All the UV glows, thermal spikes, and magnet sweeps amount to educated guesses until you test specific gravity. This physical property, the ratio of a material's density to that of water, is remarkably difficult to fake. Diamond's specific gravity is around 3.52. Zircon, heavier, measures about 4.6. Quartz and glass hover near 2.65. Moissanite, around 3.2. Once measured precisely, these numbers narrow your field of possibilities faster than any visual cue. The most reliable method available to field collectors is the water displacement test, using a fine scale, 0.001 G resolution or better, and a graduated container or syringe. Select your clean, dry candidate grain, preferably free of matrix or surface residue. Weigh it in air first, Then suspend it in water using a fine thread or a submerged basket to prevent it from touching the container sides. Calculate specific gravity using Sg equals weight in air, weight in air, weight in water. Let's say a grain weighs 0.26 g in air and 0.186 g when submerged. That yields Sg equals 0.26 / 0.26, 0.186, equals 0.26 / 0.074, approximately 3.51. This is an excellent match for diamond. Now take a second sample, similar luster, same pan location, but it weighs 0.29 g in air and 0.227 g submerged. Sg equals 0.29, 0.29, 0.227, equals 0.29 / 0.063, approximately 4.6. Zircon, same surface traits, but density tells the truth. It's crucial to repeat the measurement 3 times per grain to rule out error from air bubbles, thread buoyancy, or incomplete submersion. For grains smaller than 0.05 g, the margin of error becomes too large. Those should be grouped for aggregate Sg or sent for lab testing. Some field practitioners skip this step due to setup complexity, but it's where serious differentiation begins. A clean cluster of grains testing between 3, 48.3, 55 in Sg, non-magnetic, UV blue fluorescent, and optically sharp. That suite deserves lab priority. Note that lamproite and altered kimberlite host rocks often produce composite grains, indicator minerals embedded in weathered matrix. These will test artificially low 2, 7, 3, 0, but can still be relevant if they carry internal inclusions. In these cases, fragment the grain further and isolate subcomponents for Sg testing. Also beware of false positives caused by surface coatings. Iron oxide, clay residue, or salt crusts can skew weight. Clean candidates thoroughly with distilled water and, if needed, brief ultrasonic agitation before testing. Even after a candidate passes UV, thermal, magnet, and specific gravity tests, it can still betray itself under magnification. This is where optical diagnostics become indispensable, especially in spotting moissanite, the most convincing diamond simulant. Moissanite can mirror a diamond's luster, hardness, and thermal behavior so closely that even gem labs occasionally require advanced tools to separate them. But one flaw gives it away every time: double refraction. Under a standard 10x 30x loupe or microscope, observe a faceted edge or internal inclusion within the crystal. Diamonds are singly refractive, meaning light passes through them in a single path. Moissanite, however, is doubly refractive. It splits light into 2 paths, creating ghosted or doubled images along the edges of facets or inclusions. This doubling isn't subtle. In well-cut stones, it can create a shimmering or fuzzy appearance to facet junctions. In broken or rough grains, it causes internal features to appear blurry or layered. Use a focused light source and rotate the grain slowly under the loupe. If the facet edges seem sharp from one angle but split or blur when tilted, suspect moissanite. In rough specimens, look for parallel striations or repeated lines inside the stone, artifacts of the synthetic growth process or natural birefringence. Moissanite is also highly birefringent when viewed through a polarizing lens or dichroscope. If you rotate the sample and see color or light intensity shift between views, it's likely not diamond. Diamonds remain optically stable under polarization. Another clue lies in surface polish. While moissanite is nearly as hard as diamond, versus 10 on Mohs, its polish lines under magnification often differ. Diamonds show crisp facet junctions with minimal ripple or chatter. Moissanite facets may display slight polishing grooves, especially in older synthetic stones or hand-finished cuts. Additionally, observe dispersion, the fire or rainbow effect. Moissanite exhibits much higher dispersion, 0.104, than diamond, 0.044, which means it can appear overly flashy or prismatic, especially under halogen or daylight. This trait makes moissanite popular in synthetic jewelry, but in the field it becomes a diagnostic marker. If a candidate stone throws bright rainbows in daylight, it's worth checking for facet doubling immediately. For non-faceted roughs, examine surface texture. Diamonds, even when broken, often have a greasy luster and a slightly pitted or conchoidal fracture. Moissanite may break more cleanly and present glacier surfaces. Combine this with the lack of internal life. Diamonds often show zoning, graining, or natural inclusions that resemble feathers or wisps. Moissanite tends to be cleaner or shows synthetic-looking inclusions like curved growth lines or gas bubbles. Lastly, check transparency consistency. Real diamonds often have cloudy zones, twinning lines, or embedded minerals. Moissanite is usually optically clearer, ironically a giveaway. If a stone seems too perfect under magnification, scrutinize it harder. This final optical exam is a field geologist's last gate before lab costs begin. A grain that fluoresces blue, tests hard and thermally conductive, has SG near 3.52, and shows no facet doubling under magnification is a legitimate diamond candidate. Rare, valuable, and worthy of preservation. Discovery without discipline leads nowhere. A single candidate stone, no matter how convincing, means little unless it's part of a reproducible pattern. That's why professional diamond prospectors rely on a strict field workflow, an iterative, data-rich approach that transforms random finds into verifiable leads. Without this grid-based logic, many promising sites are abandoned prematurely or overvalued based on isolated results. Step 1 is site grid layout. Once indicator minerals or candidate stones are discovered in a specific area, say a drainage basin or slope wash, you map out a sampling grid. Start with a baseline, a single transect line perpendicular to the dominant flow of water or slope. Flag sampling points at regular intervals, usually 10 to 25 meters apart depending on terrain scale. For each point, you collect consistent sample volumes, typically 20-30 kg of surface material or float rock fragments. Every sample must be tagged, photographed, and logged. Use waterproof field books and GPS tools to record. Grid coordinates, sample weight, visible indicators or anomalies, nearby geological features, dikes, breccia zones, drainage splits, slope direction and weather conditions. Back in camp or base, each sample is processed identically. Crush, sieve usually through 20 and 40 mesh, pan for heavies, then isolate and test any suspect grains using UV, thermal, magnet, and optical methods. Concentrates are stored in labeled vials or packets and cataloged against the sample point. The goal is pattern recognition, not perfection. If one sample yields 3 pyropes, 1 chromite, and 2 thermal positive grains, and 2 adjacent points show similar results, you now have a vector. Extend the grid upslope or perpendicular to define the anomaly. If values drop off rapidly outside a narrow zone, you may be skimming the edge of a pipe or dike. Throughout this process, log any structural or textural changes in host rocks. Brecciated zones with mixed mineralogy suggest explosive emplacement, common in kimberlite pipes. If host rock transitions from unaltered granite to serpentinized ultramafic within a few meters, note it. Take slab samples for later thin section or assay work. Where terrain or weather prevents grid sampling, switch to radial sampling from a float concentration point. This is especially useful in glacial terrain or stream beds. Radiate 50-100 meters outward in multiple directions, collecting similar sample weights and processing identically. Repeatability here matters more than absolute concentration. Photographic records enhance reproducibility. Shoot every sample site from multiple angles, ground-level overview, close-up of float, and macro of interesting grains. Use a consistent scale reference, a coin, pick head, or tagged ruler, so images can be compared later or used in reports. All these steps may seem excessive in the heat or rain, but they create traceable provenance. A diamond-grade grain pulled from a logged, repeatable grid pattern with consistent indicators and recorded location holds value, geologically and financially. A one-off found in someone's jacket pocket? Worthless to most labs and buyers. At this point, you've moved beyond random hunting. You're generating data that can be mapped, retested, and scaled. But before you expand the grid or seek assays, you need to understand one truth. Even the best fieldwork can land you on a false lead. Because not every pipe is productive, and not every volcanic breccia is kimberlite. The next challenge is to confront a failure and see what it teaches about what not to chase. It's one of the hardest truths in diamond exploration. Not all kimberlite is created equal. Finding the rock doesn't guarantee it carries gem-quality diamonds or any diamonds at all. The term kimberlite describes a rock type, not a promise. Around the world, thousands of kimberlite pipes have been mapped, yet only a fraction are economically viable. Understanding the limits of kimberlite's range, both geographically and mineralogically, is the dividing line between amateur enthusiasm and professional strategy. Start with the basics. Kimberlite occurs almost exclusively in ancient continental interiors known as cratons, regions of thick, stable lithosphere that have resisted tectonic disruption for over 1 billion years. These deep roots, often exceeding 150 km in thickness, are the crucibles where diamonds form. The oldest cratons include the Kopval in southern Africa, the Slave and Superior in Canada, the Siberian, São Francisco in Brazil, and parts of Western Australia. If you're not on or adjacent to one of these cratonic blocks, the odds of finding a true diamondiferous kimberlite drop drastically. Within those cratons, kimberlite pipes typically align along ancient fault lines or deep-seated fracture zones. These weak spots allowed volatile-rich magma to erupt explosively from mantle depths, creating carrot-shaped pipes or narrow dikes filled with fragmented ultramafic rock and mantle debris. The surface expression of these pipes varies. In South Africa's Kimberley region, weathered pipes form shallow depressions. In Canada's Northwest Territories, they sit buried under tens of meters of glacial overburden. In both cases, indicators, pyrope, chromite, ilmenite, pave the way long before kimberlite itself is visible. Yet only about 10–15% of kimberlite pipes contain diamonds, and fewer than 1% are rich enough to mine. Why? It comes down to mantle sampling and thermal history. A kimberlite must intersect a diamond-stable region of the mantle, known as the diamond stability field, and rise to the surface fast enough over hours to preserve the diamond structure. If the eruption is too slow, or the source mantle too warm or depleted in carbon, the diamonds either never form or are destroyed during ascent. That's why even in rich fields like the Kopval or Slave Craton, exploration teams drill dozens of pipes to find one worth testing. They analyze bulk samples, up to 100 tons, to estimate diamond concentration, carats per 100 tons or CPHT, size distribution, and stone quality. Many pipes yield only microdiamonds, particles under 0.5, that prove diamond potential but have no market value. As a field prospector, you'll often encounter weathered kimberlite float or matrix that looks promising, soft, altered, full of indicators. But unless that float is part of a mapped system or tied to a productive source, it's just that, float. Mapping float trails back to a pipe or dike is essential, and repeating mineral patterns across multiple samples matters far more than a single, hot pan. Take Canada's Lac de Gras region as an example. Over 200 kimberlite bodies were discovered through indicator tracking and geophysics. Only a handful, like Ekati and Diavik, became mines. The rest were subeconomic, too deep, or lacked sufficient diamond content. This is why discovery doesn't equal value. The mineral suite may be identical, but the diamond cargo differs wildly from pipe to pipe, even within a few kilometers. You must also watch for misidentification. Some serpentinized ultramafic rocks or carbonatites mimic kimberlite superficially, same greasy texture, same mineral peppering, but they originate from different depths or lack mantle-derived inclusions. They may yield pyrope or ilmenite, but without eclogitic nodules, chrome diopside, or peridotite xenoliths, the diamond odds plummet. This is the sobering side of kimberlite's real range. It's not just about finding the rock, it's about locating the right rock in the right place with the right ascent history. The failure to do so is what derails many early expeditions, but the story doesn't end there. In the late 1970s, prospectors working the remote East Kimberley region of Western Australia stumbled onto a volcanic rock that didn't match the textbook image of kimberlite. It was vesicular, altered, glassy in parts, and rich in mica, too potassium-heavy, too chaotic. Early samples showed indicator minerals, but the host rock failed traditional classification. It wasn't until microdiamonds appeared in concentrates and bulk sampling confirmed a rich grade that the curveball hit. The deposit was not kimberlite, it was lamproite. And it held what would become one of the most prolific sources of pink diamonds in the world, the Argyle mine. Lamproite shattered assumptions about what a diamondiferous rock could look like. It forms through low viscosity, volatile-rich eruptions, often at shallower depths than kimberlite, and carries a different geochemical fingerprint. High potassium, elevated magnesium, and distinct mineral inclusions like leucite, phlogopite, and perovskite. Unlike kimberlite, lamproite doesn't always conform to the deep craton model. Some productive lamproite bodies, including argile, occur near the edge of stable cratons or in reworked cratonic zones, broadening the range of viable terrains. In the field, lamproite can easily be missed. It's often mistaken for weathered basalt or volcanic tuff. Its key diagnostic features include vesicular texture, gas bubbles frozen in the matrix, often glass-lined or filled with secondary minerals. Oily to greasy luster. Unlike kimberlite's earthy surface, lamproite often looks slick or resinous when broken. Sulfur smell. When freshly split or wet, lamproite may emit a faint, rotten egg odor due to residual volatiles, something kimberlite almost never does. Greenish or pale yellow tone. Lamproite can range from tan to olive, often with embedded mica flakes or reddish iron patches. Indicator minerals also differ. Lamproite concentrates may contain phlogopite, a bronze-colored mica that breaks into flexible flakes. Perovskite and leucoxene, brownish accessory minerals detectable in heavy separates. Olivine and chrome spinel, common but not always associated with diamond content. Because lamproite is softer and more chemically reactive than kimberlite, its weathering footprint tends to spread wider. That means indicators may disperse further downslope, diluting signal concentration. In sampling, this requires wider grid spacing and more emphasis on float trails than direct outcrop. The real curveball? Lamproite's diamonds tend to be smaller, more included, and variably colored, but still commercially viable. Argile's stones rarely met high gem-grade clarity, but the intense pinks, purples, and reds fetched extreme premiums due to rarity. This reframed the value logic. Even low-grade, high-volume pipes could succeed if the product was unique enough. Field testing lamproite demands more patience. It responds poorly to thermal probes due to alteration and rarely shows strong magnetic traits. You must rely on the heavy mineral sweet, UV reactivity, and crucially, density testing. Lamproite concentrates tend to contain light matrix mixed with denser grains, requiring careful sieving and multiple panning passes to isolate anything diagnostic. In sum, lamproite teaches an essential lesson. Diamond host rocks can hide in plain sight, especially when they violate expectations. A brecciated vesicular green rock with odd mica flashes, easily overlooked, might outclass a textbook-perfect kimberlite in diamond yield. But that also means more pipes go unnoticed by those who test only for the conventional. This pivot opens the door to a deeper problem. What happens when a field site delivers promising indicators, matching textures, and even candidate stones, but the lab returns nothing? The answer isn't just disappointment, it's a full reversal. Because sometimes the rocks are real, but the sample was.